Hello, Space Cadets. Today, we're diving into the amazing world of nuclear physics. It's a realm where atoms rule and particles smaller than you can imagine zip around at incredible speeds. Our journey begins in the early 20th century with a scientist named Ernest Rutherford. He conducted an experiment that changed our understanding of the atom forever. Picture this. Rutherford and his team fired tiny, positively charged particles called alpha particles at a thin sheet of gold foil. They expected the particles to pass straight through the foil with little deflection. After all, the prevailing model of the atom at the time was like a plum pudding, with electrons scattered randomly throughout a positively charged sphere. But hold on, something astonishing happened. While most of the alpha particles did pass straight through, some were deflected at large angles. A few even bounced straight back. This was as shocking as throwing a tennis ball at a piece of tissue paper and seeing it rebound. Rutherford realized that the plum pudding model couldn't explain these results. He proposed a revolutionary new model. The atom was mostly empty space, with a tiny, dense, positively charged nucleus at the center. The electrons, he suggested, orbited this nucleus like planets around a star. This groundbreaking experiment paved the way for our modern understanding of the atom. This experiment, my friends, was just the tip of the iceberg. It opened up a whole new world of subatomic particles and nuclear processes, including the mysterious and powerful alpha, beta, and gamma radiation. For instance, alpha decay can be represented by the equation, where uranium-238 decays into thorium-234, and an alpha particle, which is a helium-4 nucleus. And don't forget about antineutrinos, those elusive particles that play a crucial role in beta decay processes. So what exactly are these mysterious rays, you ask? Well, imagine the nucleus of an atom as a tightly wound spring full of potential energy. Sometimes this spring can unwind, releasing energy in the form of particles or waves. This process is called radioactive decay. And the energy released comes in three main flavors: alpha, beta, and gamma radiation. Alpha radiation is like a lumbering giant, big, slow, and carrying a positive charge. It consists of 2 protons and 2 neutrons, essentially the nucleus of a helium atom. Beta radiation, on the other hand, is like a nimble sprinter, small, fast, and carrying a negative charge. It consists of high-speed electrons. Finally, gamma radiation is like a bolt of lightning. Pure energy in the form of electromagnetic waves. Think of it like this. Imagine you have 3 superpowers. Alpha radiation is like having super strength but being slow. Beta radiation is like having super speed but not much strength. And gamma radiation is like having the power to shoot lasers from your eyes. Each of these types of radiation interacts with matter in different ways, and understanding these differences is crucial for both harnessing their power and protecting ourselves from their potential harm. Now, before you start thinking that radiation is all doom and gloom, let me assure you that it plays a vital role in our everyday lives. From medicine to industry, radiation has become an indispensable tool for the betterment of humanity. In medicine, radiation is used in a variety of ways, from diagnosing and treating diseases to sterilizing medical equipment. X-rays, a type of electromagnetic radiation, allow doctors to see inside the human body without surgery, helping them diagnose broken bones, detect tumors, and monitor the health of our organs. Radiation therapy, using high-energy rays like gamma rays, is a common treatment for cancer, targeting and destroying cancerous cells while minimizing damage to healthy tissue. Radioactive isotopes, atoms with unstable nuclei that emit radiation, are also used in medical imaging and diagnostic tests, allowing doctors to track the movement of substances within the body and diagnose a wide range of conditions. Beyond medicine, radiation finds applications in a surprisingly diverse range of fields. In industry, it's used for gauging the thickness of materials, detecting flaws in welds, and tracing the flow of liquids and gases through pipelines. In agriculture, radiation helps develop new plant varieties, control insect populations, and preserve food. Even in archaeology and art history, radiation comes to the rescue, helping determine the age of ancient artifacts through radiocarbon dating and revealing hidden details in priceless works of art. So you see, radiation, when used responsibly, is not something to be feared, but a powerful tool that benefits humanity in countless ways. Let's delve a little deeper into the fascinating world of alpha particles. As mentioned before, they are like the lumbering giants of the radiation world, consisting of 2 protons and 2 neutrons bound together, just like the nucleus of a helium atom. They are relatively large and heavy compared to other types of radiation, and they carry a positive charge, which means they are attracted to negatively charged particles and repelled by positively charged ones. Due to their size and charge, alpha particles interact strongly with matter. They lose energy quickly as they travel through a material, bumping into atoms and ionizing them by knocking off electrons. This high ionizing power makes alpha particles potentially harmful if they get inside the body, as they can damage DNA and other biological molecules. However, their large size and charge also mean they have low penetrating power. They can be stopped by a sheet of paper, a few centimeters of air, or the outer layer of our skin. This makes alpha radiation relatively safe to handle as long as it remains outside the body. In fact, alpha particles are used in some everyday applications such as smoke detectors. A small amount of americium, 241, an alpha emitter, ionizes the air inside the detector, creating a current. When smoke enters the detector, it disrupts this current, triggering the alarm.